Welcome! The purpose of this study is to compare and evaluate different compressed air solutions when air demand is highly fluctuating. In particular, we are going to examine 5 differently variable flow profiles, and we are going to evaluate 6 alternative compressor solutions, defining some guidelines in order to determine the best system. The first case considered is this one, where the customer has a very high flow fluctuations between night shifts and day shifts, between approximately 30 cubic meter per minute and 220 cubic meter per minute. Another way of representing previous flow profile is the flow spectrum. On y-axis you find the requested flow as absolute figure on the left, and as percentage of the maximum requested system flow on the right. The x-axis shows the time as percentage of the period of observation. As you can see, this system has a high variability, in this case up to 90%, and also a flow less than the average flow is requested for a long time, in this case almost 50% of the time. This flow spectrum refers to a production site with 2 6-hour night shifts with low air demand and 2 6-hour day shifts with high air demand. In this other slide, we see other 2 cases analyzed. Case number 2 still refers to a highly variable spectrum with 90% of variability, but compared to case number 1, less than the average flow is requested for only 30% of the time. This is typical for a production with 1 8-hour night shift with low air demand and 2 8-hour day shifts with high air demand. The third case that will be considered is the following. A case with lower variability than case number 2, only approximately 65% of the flow instead of 90% of the flow. And to differentiate it from the previous 2 cases, we call this case with medium variability. As for case number 1, this variability occurs for a long time, as less than the average flow is requested for 50% of the time, or a bit more. In this slide, we see the last 2 cases. Case number 4 still refers to a medium variability of 65% of the maximum flow, but compared to case number 3, less than the average flow is requested for only 30% of the time, or a bit more in this case. The 5th case is a case where the requested flow continuously changes, but variability is only around 30% of the maximum flow. The variability occurs for all the 24 hours a day, and this is typical for an almost constant production. As mentioned earlier, the research has analyzed the energy consumption in all the 5 cases just explained before for the following solutions. The first solution has 1 centrifugal compressor and 1 large 700 kW variable speed screw compressor, whose maximum flow is the half of maximum system flow demand. The second solution considers 2 centrifugal compressors, whose maximum flow is the half of maximum system's flow demand. As you know, centrifugal compressors can be designed for best efficiency, but with a lower regulation range, or alternative, for a wide regulation range, also called turn down, but with a lower design efficiency. In this second solution, compressors are designed for peak efficiency, and they also have the latest and most efficient load sharing control. The third solution considers, in this case, two centrifugal compressors designed with wide regulation range. Also in this case, like for all the next solutions with multiple centrifugal compressors, the load sharing control is always foreseen, since this control system allows always to reduce the blow-off of the centrifugal compressors by extending the system's regulation range. The fourth solution considers three centrifugal compressors whose maximum flow is 1/3 of maximum system flow demand, and the centrifugal compressors are designed for wide turn-down, and they have, again, load sharing control. The fifth solution considers again mixed technologies, but in this case there are two centrifugal compressors with load sharing control and one small 160 kW variable speed screw compressor. In this case the compressors are not controlled by a scheduler. It means that the small variable speed rotary is used only to cover the air demand peaks. The sixth and last solution considers the same compressors as solution E, but in this case the three compressors are controlled by a scheduler. The scheduler allows to operate, for example to load or unload or switch off each compressor according to a predefined schedule in order to optimize the system from various points of view. In this case, we want to optimize the system from the energy consumption point of view. Coming back to our original flow profile, the solution A with centrifugal compressor and one large variable speed rotary compressor allows to exactly match, like you see here, the flow requested by the system. For this reason, it is usually claimed to be an unbeatable combination, as there is no wasted air. But what we have to establish is whether it is also the most efficient solution from an energy consumption point of view. This is the solution B with two centrifugal compressors designed for peak efficiency. Compared to a solution with two centrifugal compressors where the compressors have no load sharing control, the load sharing control allows to extend the system's regulation range, reducing therefore the blow-off, like you have seen here. If we use two compressors with a wider regulation range, like in solution C, the blow-off can be further reduced. And this is the fourth solution with three centrifugal compressors, designed for wide turn-down with load sharing control. This is the fifth solution with two centrifugal compressors with load sharing and one small 160 kW variable speed screw compressor. In this solution, the three compressors are not controlled by a scheduler, and the variable speed compressor is used to cover the peak of air demand. And finally, this one is the same solution, but with a system scheduler. In this case, if the flow pattern is repeatable over the days, we can use a simple time-driven scheduler. Otherwise, it would also be possible to use a flow-driven scheduler. As you have seen in these last charts, there are solutions where the air blow-off is minimum, very close to the zero blow-off system that we have seen with the solution A, with one centrifugal compressor and one large variable speed screw compressor. Nevertheless, remember, it is not the minimization of the air blow-off that we should target, but we should target the minimization of the energy consumption. Now, making the math at a pressure of 8 bar gauge, this is the comparison of the daily energy consumption for our flow pattern of case number 1, with high variability for long time. as well as the relative efficiency between the system A, the one that was supposed to be the unbeatable solution, and the other 5 systems. The efficiency of system A is taken as a reference and equals to 100. As you can see, the system C with 2 centrifugal compressors with wide regulation range and load sharing control, despite some air blow-off like we saw in the previous chart, is only 0.3% worse in efficiency compared to system A, and the system F with 2 centrifugal compressors and 1 small variable speed screw compressor with scheduler allows to save almost 3% compared to system A. If we consider 300 days per year and an energy cost of 0.1 euro per kilowatt hour, we come at the following energy cost comparison. System A allows to save approximately 1,500 euro versus system C. So the first question is, would you really prefer to have 2 completely different compressors with different spare parts for a saving of only 1,500 euro per year? And what about if you would like to have a backup compressor? Which one would you buy? The centrifugal type or the variable speed screw? The solution C has not this problem because the 2 centrifugal compressors are exactly the same. So the third compressor would be equal to the other 2 using the same spare parts. If really your main target is energy saving, and you accept to have different technologies, then consider system F with 2 centrifugal compressors and 1 small 160 kilowatt variable speed screw compressor with scheduler. This system delivers more than 15,000 euro savings per year compared to system A. But let's consider now also systems flexibility. What would happen with the 6 solutions if over the years your production changes and you do not have anymore the same daily air consumption as in the case number 1? This is the efficiency comparison between the 6 systems for the previously shown case number 1. A negative red or orange percentage indicates that the system is less efficient than the system A with 1 centrifugal compressor and 1 large variable speed screw compressor. Vice versa, a positive and green figure indicates that the system is more efficient than system A. Yellow means the 2 systems are more or less equal. This is the comparison for the case number 2, the case characterized by the same high variability but for less time. For example, we said in the case your plant has 1 night shift with low air demand and 2 day shifts with higher air demand. And here is the case number 3 with a medium variability. Remember 65% instead of 90% of the previous 2 cases. But the variability is again for long time. This is the comparison for case number 4, the one with medium variability for medium time. And this is the last case with a continuous low variability of 30% of the maximum system flow demand. So, which one is the overall best system? Are you still convinced that system A is the unbeatable and the best solution in terms of energy consumption? Personally, I would rank the system as follows. In fact, in the case number 1, the one that we took as reference, system F allows to save 15,300 euro per year versus system A. System C, yes, it has just a bit of higher operating cost versus system A. But for just 1,500 euro savings per year, for the reasons explained before, it means spare parts availability, backup compressor and so on, I personally would rather prefer to have two identical machines in my plant instead of two different machines. Moreover, if you consider also the flexibility of the systems, in the case your production will change, you can see that in case your production will grow requiring less flow variability, like in the cases from 2 to 5, system C and F allow to save 24,500 euro per year and 39,500 euro per year respectively compared to system A. The best solution in terms of energy saving is then not the solution with one centrifugal compressor plus one large 700 kilowatt variable speed screw compressor, as someone could commonly believe, but the combination of two 100 cubic meter per minute centrifugal compressor with a load sharing control system plus one small 160 kilowatt variable speed screw compressor, everything controlled by a master scheduler that runs the optimum combination of compressors according to the different needs, like in the case here depicted. Back to case number 1, the one with 90% of variability of air demand. How is it possible that the system A, that is able to deliver exactly the airflow requested by the system without any air blow-off, has almost the same efficiency as system C that has some air blow-off, like we see in this graph? The answer stays in the following two slides. This slide compares the specific power at 8 bar gauge of different centrifugal models with large variable speed screw compressors. Note that each green dot or each green square for the centrifugal represents the specific power of one single machine at design flow only. It is not a curve over all the regulation range as for variable speed compressors. As you can see, a 75 cubic meter per minute centrifugal compressor, when it works at the design point, is almost 20% more efficient than a 500 kilowatt variable speed screw compressor. A 115 cubic meter per minute centrifugal, almost 15% more efficient than a 700 kilowatt variable speed screw compressor. And the 140 cubic meter per minute centrifugal, again almost 20% more efficient than a 900 kilowatt variable speed screw compressor. So it should be clear to anybody that what you can waste in terms of energy when a centrifugal blows off a bit of air is highly compensated by what you save against the variable speed screw compressor when the centrifugal compressor works near its design point, or in general in its full regulation range. In fact, if we plot the specific power of, for example, this centrifugal compressor, which is the compressor used in our solution C, also in its regulation range and also when blowing off, we see that the specific power remains better for a range even wider than just the regulation range. It is therefore clear that only the knowledge of the real weight in terms of percentage of time of the different operating conditions allows to determine if the use of large variable speed compressors is really convenient or not. To clarify this very important concept, I want to make you another case. There was a customer with 5 old centrifugal compressors of different sizes between around 70 cubic meter per minute and 100 to 120 cubic meter per minute. Last year, the customer called us and said that they wanted to renew their compressor room to reduce their operating costs. They said that an audit was performed and that the first step they decided to do to improve their system's efficiency was to replace one centrifugal compressor with a 400 or 500 kilowatt variable speed screw compressor. I then started investigating why and how they came to this conclusion. After several questions, I finally got an answer. During some mornings, they said, between 8 a.m. and 10 a.m., they had to shut down one production line to change the tooling for the production of the type of glass they wanted to produce for the following day or days. During these 2 hours, they had an excess of air of 60 cubic meter per minute. And since the old centrifugal compressor was able to regulate only 20 cubic meter per minute, they were blowing off 40 cubic meter per minute of air. By replacing this compressor with a 500 kilowatt variable speed screw compressor, they said, they would have been able to avoid any blow-off, improving system efficiency and reducing therefore their operating cost. This was unfortunately a completely wrong approach, as I am going to show you hereafter. This is the specific power comparison at 4-bar gauge between a 2-stage centrifugal compressor and a 2-stage 500 kilowatt variable speed screw compressor the customer wanted to buy. The green point represents the specific power of the centrifugal compressor at its design point, and the dotted green curve shows the specific power when the same compressor is regulating. As you can see, the variable speed screw compressor the customer wanted to buy to avoid the air blow-off is more than 40% less efficient than an equivalent centrifugal compressor. Even if the centrifugal compressor is blowing off 13 cubic meter per minute, it is still more efficient than the variable speed screw compressor. So the right consideration the customer should have done to choose the right machine should have been, first, to evaluate the cost of blowing off 40 cubic meter per minute for 2 hours per day. And this can be easily done using this formula. So the yearly cost of this wasted air is in the worst case 12,000 euro per year. I say worst case because in reality the customer said that not all the days, not all the mornings they had to change the production lines. Also, 2 hours continuous blow-off could be simply avoided if a load-sharing system with anti-blow-off were installed, reducing the 12,000 euro per year to few hundreds of euro. In any case, let's leave 12,000 euro per year. Then, the second step he should have done is to calculate the extra cost for using for the 22 remaining hours per day a compressor that is 43% less efficient than another one. And the cost is around 110,000 euro per year. So, to avoid wasting 12,000 euro per year having some blow-off in the morning, the customer would have spent 110,000 euro per year more by using a compressor which was 43% less efficient than another one. Even if we consider that maybe for the 22 hours per day the variable speed screw compressor does not work always at full load, the difference is so huge that it would be hard to affirm that the customer would have saved energy and money by buying a 500 kilowatt variable speed screw compressor instead of a new centrifugal compressor. So, in conclusion, some guidelines or recommendations. Never assume which is the best solution. There is no magic solution for all the cases. Always ask for an error assessment first, but make sure it is also read and interpreted in the correct way. Remember that centrifugal compressors can be more efficient than large variable speed screw compressors, even if they are blowing off some air. Each case is then customer specific and needs to be evaluated considering several aspects, the most important of which are compressor's overall efficiency, and with overall I mean not only at full load but also at partial loads, system's flow profile and flow spectrum, because it is fundamental to know how much time the compressor will work in one operating condition, for example close to the design condition, and how much time it will work in another condition, for example blowing off a little bit of air. And then other aspects like installation requirements, floor space, need for backup units, and or need for spare parts stock, and then system flexibility in case of different future production needs, and of course initial capital investment and other aspects that could occur case by case, influencing therefore the right solution. So that's all. Thank you for your attention. Should you wish some more information, do not hesitate to contact me at the email address below, nicola_piccardo@eu.irco.com. And also a special thanks to my colleague Marco Tobia for the contribution he gave to this study.